Hi everyone, welcome. I'm Yiannis. I represent the ProbeLab team, and today I'm going to talk about a set of tools that we have built to monitor the health of the Ethereum peer-to-peer network. Why we're doing this? Because we believe that things generally might be working, but not necessarily in ways, in the way that we think they do. So we think that we should generally be looking deeper into how things are working. And we argue that the peer-to-peer layer of the Web3 ecosystem of several blockchains has received a lot less attention than it should have. There is a ton of on-chain metrics and dashboards, but very little has been done on the peer-to-peer layer, which is under everything else. So we argue that if something breaks at that layer, then everything above it, all the great stuff that people are building and presenting, is just going to come crashing down. So if I had to say in one sentence, what we're doing is that we're carrying out rigorous measurements on the peer-to-peer protocol stack in order to make the network layer better, faster, and safer. And we think that's what is needed in order to guarantee a robust layer below all of the other stuff that is building on top. Now, over the years, we have built a set of tools, starting from more kind of high-level topology and network structure items, and going deeper into critical components monitoring and uptime monitoring and so on, and then going deeper into more detailed and sophisticated things like data availability challenges that the community is trying to overcome at this point. I'm obviously not going to cover everything, but just going to focus on a few of those tools to go through and let you, give you an idea of what they are and the related pointers. So starting with network topology, you might have heard of or used the Nebula crawler, which is a very well-known crawler by this point. It started off as a crawler for the IPFS network, but has now expanded and supports many other libP2P based networks, but also disk v4 and disk v5 networks, such as the Ethereum consensus and execution layer. The one thing that makes Nebula, come apart is that it's not only crawling the network, it's also monitoring the liveness of nodes. So it's going and, crawling networks, finding peers, and then pinging them every so often after a while, like continuously, and therefore we can find things like peer churn and so on. So let's start with a quiz to see what we can find out from things like a simple crawler and all of the other things that are built on top. So which Ethereum consensus layer client do you think is least dependent on centralized cloud infrastructure? Loads. Yeah, others? Okay, that was correct actually. The last one, Nimbus, is the one. Well done to the team. So if we see, so at the top here, it's not shown very well, but it's Lighthouse, Prism, and Lodestar, and at the bottom is Techo, Grandine, and Nimbus. So if you see it in terms of percentages, obviously Nimbus is the least dependent, but of course it's not the most popular client. So it depends a little bit on how you do it. The blue line here is the data center, those that are deployed on data centers, and the orange one is those that are have got custom deployments. So you can find other things like what's the most popular chain on Optimism? Any ideas, anyone? Sorry, Base? No. This is a pretty recent result, and we found that is actually Unichain by far. So yeah, this is pretty recent. If you think we're missing something or not, we can come talk to us. We can argue and have another look later. to figure out if we're correct or not. So yeah, these are things that you can figure out if you look a little bit deeper into the network, and that's what we're actually doing. So carrying on again on the network topology, we have recently built a tool called ants, which like ants, when you release them and when they're out, they're covering a big footprint. So what we're doing is that we want to release ants in DHT structures so that they can monitor specific things, but specifically DHT client requests. So we spread ants on approximately every 20 DHT server nodes, and that way we're able to gather information from all the requests from the network. The tool is automatically adjusting, so if the network size doubles, then the number of ants that are going to be out in the network is also going to double. And we're currently supporting the Celestia network, but soon there's going to be more. So briefly how it works is that you see, we can assume this is the DHT key space. These are regular DHT server nodes. The green ones are the ants that we are putting in the network, as I said, roughly every 20 DHT server nodes. And therefore then what happens is that when a DHT client comes in order to do several processes that it needs in the network, among others, update its routing table, it's going to ask other nodes around. So we want to make sure that one of these green nodes is among the 20 peers in the network where the DHT request is going to end up through. So in that way, we're kind of, it's honeypot of sorts that is gathering requests. Now, with this, as I said, it was great to see how we were able to figure out what's the light node population in the Celestia network. We don't have results yet, but it's soon going to be on ProbeLab.io. So if you want to know more about that, that's the thing to monitor, or you can come talk to us afterwards. Now, going into protocol performance. We have recently built a tool called Herms, which is basically a gossipsub listener and tracer. The measurement goals of building that was to figure out metrics related to message propagation, latency, number of duplicate messages that a node is receiving, the validator node bandwidth consumption, and several others. So in doing that, we didn't want to run a full Ethereum node for several reasons. What we instead wanted to do is have a lightweight libp2p host, which would spin up, establish connections, stay connected, and then participate in the network in this way. Herms is tracing all of the events, so from the libp2p host events like connections and disconnections to gossipsub trace events which were of particular interest to us, like grafts and prunes, and like in the off nodes in the local mesh network, subscriptions, I have and I want messages for the gossiping function of the protocol, and then go deeper into peer scoring and things like that. So we were able to gather all of this data, and this helped us look into lots of important metrics for the network for a protocol for gossipsub that is very critical, right? It's, as you might know, it's transferring blocks and messages in the Ethereum blockchain and other blockchains as well. This is roughly what the architecture looks like, but I'm not going to stay in this slide because that's just one way of doing it. There might be several others, and even this might evolve over time, but this is what we used for deploying Herms on the Ethereum network. Now, briefly some results. So we wanted to see the number of duplicate messages, and in this plot there you see the number of duplicate messages on the x-axis, so it goes from 0 to 10, and the message ID, the CDF of messages on the y-axis. So if you look at the green line, it's representing the blocks topic, the block topic, and we see, for example, that around 55% of messages are being delivered to the same node 4 times or less. So on the one hand, we like seeing this result, one might say 4 times is quite a lot. On the other hand, we should not expect to have, 0 duplicates, because this is not a client-server architecture here. It's a peer-to-peer network, and having duplicates in many cases helps in case, for example, of an attack where someone is trying to delay delivering messages or eclipsing a node. So it's good to have some duplication, but we're seeing that as, when we're going to 6 or 8 duplicates per message, that might be a little bit too much. So we figured out that things are working well, but there is still some space for optimization. On another bandwidth-related metric that we've seen, this is on the x-axis all the message types, and on the y-axis is the percentage in terms of kilobytes from the total. And we found out that I-have messages represent 33% of the total bandwidth of a node, which is quite a lot, and there might be, again, some of it is expected, but there is clearly some space for optimization. You'll find all of the reports that we've done on ETH Research. If you go, it's all of these studies, you can scan them, but also under the networking category. They're pretty recent, the last few months, so you can take the full picture of all the things that we've managed to find. Now, moving on to another tool that we have recently built. It's called UCLA, a network bandwidth monitor. We might have to change the name, but that's what we have for now. So the methodology is that as we run Nebula and we have a list of online peers, we then deploy Herms and try to connect to those peers and keep stable connections. And then eventually we're trying to download a carefully chosen volume of data from each node, so that on the one hand, we do not overload the node that has got other things to do, like these are main nodes that are doing their thing. And at the same time, we are able to kind of momentarily saturate the bandwidth of the node so that we know how much bandwidth they've got available. We're seeing in this graph here on the x-axis is the slot duration from 0 seconds to 12, and on the y-axis is the bandwidth in megabits per second. So interestingly, we're seeing that there are some like dips in the bandwidth availability. The blue line, especially for the blue line, which represents cloud nodes, whereas the orange one is for non-cloud nodes. So seeing these dips there means that there is a little bit of extra bandwidth availability, which could be very interesting for engineering teams if they want to, for example, push some more data out during some particular, time within the slot. Then this could be chosen. And this, I believe, it's going to become very helpful as as we're going towards peer DAS and the blob count increase and all of those challenges where it's not exactly clear where bandwidth availability can come from in order to accommodate bigger blobs. So on the one hand, nitty-gritty details. On the other hand, we believe that measurements is not really an end, but only a means to an end, which is to go towards protocol optimization and network architecture optimization, and that's how we're helping here. So yeah, to recap, quite a few tools. We've covered some of them only, and again, we're going from network topology and structure into more detailed things, and in most cases, we end up having to use several of our tools as we go along. So as I mentioned, having Nebula gather a list of peers, then using that to inform other tools to go and connect with those peers, and then go from there deeper and deeper. And we believe there is lots more that can be done. So looking ahead, we obviously are collecting data for a number of networks for a number of years now. So we have a kind of data warehouse of sorts, which we want to make available to the community. So we're building an API. We know that other teams are interested to get the data and deploy into their own models to do energy sustainability metrics and risk modeling and things like that. So this is under active development right now. We want to integrate more networks, as you know, with some of them on the pipeline already. We want to repeat a NAT traversal study that we have done a few years ago on P2P to figure out the capability of the NAT hole punching component, and then more generally focus on the challenges to deal with data availability sampling on Ethereum and other networks. So if you head to ProbeLab.io, you're going to find out weekly reports for the networks that we're currently monitoring. You're going to find other reports like block propagation latency for the Ethereum network, and then links from there to our methodology and all of the tooling. Yeah, and as I mentioned, of course, some of the results results of the studies are on ETH-Research. Yeah, and ProbeLab.network has got some more information about our team. Yeah, and now, thank you very much. I'll now pass it on to Dennis to do a little demo of one of the tools, the bandwidth measurement monitoring tool, to see what bandwidth looks like on this Wednesday afternoon.
All right. Hi, everyone. My name is Dennis. I'm also from the ProbeLab team. Okay, yeah. All right. Can you see my screen? Yeah, there we go. Okay, it's loading, sorry. Here we go. Cool. So Yiannis introduced you to Ookla already, and to spice it up a little bit, I wanted to try a demo to show what the data looks like that we gather. I mean, this data won't be representative, of course, because we're running it from this convention center Wi-Fi, but still, I think it should be interesting to you to see what data we gather. So if we run Ookla, this is our bandwidth measurement tool, as you have heard. You can pass in a few command line parameters. For example, in this case, we query 10 peers from our Nebula database, which are peers that are online in the Ethereum network. We request from each of these 10 peers 2 blocks. And if it fails, we do 3 retries. And because we're running quite a few of these Ookla runs every day, you can also give it a tag from where you have run it. For example, we are currently running it from US East 1, but you could also in AWS, but you can also run it from different geolocations, for example. And I just give it a tag of Devcon Devcon demo, or let's leave it the P2P for now. So right now, okay, of course, the demo daemons. It's always the same. Sorry. So we are running a full Prism node in the on one of our instances in the cloud, and Herms, as you have known, is part of Ookla, which is running underneath, so which we build upon. It needs to connect to one of these full nodes. So I'm just forwarding the port here. Let's try it again. So it's launching the Herms node. And I want to emphasize Herms is quite modular. So if you require for your networks, for example, bandwidth measurements, Herms could be extended to also work for your network if you have bandwidth measurement requirements. So let's see. Okay. So basically what it does, I can talk over it. It will basically just connect to the nodes, download the blocks, and maybe in the meantime, I have only 2 minutes left. I've run it earlier, so we might be able to take a look at. Okay, it's all not working, of course.
So meantime, I encourage the audience to connect to Meerkat app, and you can ask questions.
Hang on. Let's see. Okay. I hoped it would work, and I practiced a lot. Of course, it's not working. Let's try it again. Okay, maybe you can ask questions, and I try to run it in the meantime.
Yeah.
You will answer the questions?
Yeah.
So
here we go. It's working. So it's connecting to nodes, downloading. Yes, thank you very much. So it's now connecting to nodes, downloading blocks, and measuring the bandwidth that these nodes have available to get a distribution of what bandwidth is available in the Ethereum network, which then would inform protocol decisions around, for example, data availability or block sizes that we could increase to some certain degree, and so on. The next step would have been that we look into the database, but it looks like my computer is frozen here. So maybe maybe that's already enough to showcase that it's working for now, and maybe go on with some questions, Yiannis.
Thank you.
Okay, yeah, we have a first question.
Yeah.
And how many nodes do you need to run yourself to get a complete picture of the network?
Okay, I don't know for a complete picture of the network, I guess, is that for the ANS? If complete picture of for which tool, basically? I don't, that's why I don't.
Yeah, if the person is in the audience. Okay, so can you pass the micro?
Thank you. Yeah, I was just wondering, more in general terms, for all the tools, everything to get all the data you need, like besides the crawler for ants or for anything like that, how many nodes do you run yourself in order to get access to the networking and data? Or can you just use public nodes and connect to that?
Right, so it depends on the tools. Like we do have, for example, the Nebula crawler is running 24/7 for several networks. We have some other tools like to monitor the DHT lookup time of the IPFS DHT, amino DHT, and that is running from several locations, from 7 locations around the globe, I think, again, running 24/7. Yeah, I don't know if that answers the question. For the ANS architecture in particular, for the Celestia network, we're running something between 5 and 7 nodes, I think. It doesn't need more because it can cover more space. Yeah.
Yeah, that makes sense. Thank you very much.
Thank you. Yeah.
Let's go through a couple more questions and then return to the demo.
Yeah.
So,
Can I run these tools within Kurtos's local networks? I guess the answer is yes here.
Depends. So I'm not familiar with Kurtosis and the networking set that it's using.
Hey, yeah, you can configure Kurtosis so that it exposes the ports outside of just the network that in Docker. So it essentially exposes it on the host.
Yeah.
And then, yeah, all of the stack will work.
Yeah.
I think another interesting question is if these tools can be used in a custom lib P2P network, the second question.
Yeah, generally the answer is yes. It's not as, like most of the tools that we're building are for libp2p based networks. So it's going to be a lot easier than building a new tool from scratch. That being said, some things depend on like the network characteristics and how the whole protocol is set up. It's not a matter of just changing one parameter and adjusting to another network, but we have done, I think, a very careful job of making it easy to integrate more networks.
Okay, and one more question. What stops someone from using Ookla to grieve the network?
Which one?
First one.
Yeah, that right now it's not open source. I think that's the easiest answer.
That's how we stop. Yeah.
Okay, I think we don't have much time left, so let's just transition back to the demo.
Yeah, I just want to briefly show the data that we
It's a good question, though, this one, because we are planning to make it open source, so we'll think about it.
Yeah. Okay, cool. So you can see the database. So as you've just seen, it has run, and you can see that there are 2 studies now because I ran it right before the talk, and it was working. And so the second one here is the second study that we just started. Here you can see the tag that we gave to it, and then each connection to an Ethereum node results in a visit, in a bandwidth visits, how we call it here. And yeah, here you can see all the data that we gather here. So how, in which time of the slot did we request the data? So you can imagine that in different times of the slot, the bandwidth might differ because you have to do other duties here. if the connection was successful, which blocks we requested from that other node, the compressed number of bytes, but also the uncompressed number of bytes, the bytes that we sent over the wire, so with all the enveloping and so on, and how long it took, and then the resulting megabytes per second. And yeah, the round trip time and how many retries we needed. And so this goes even beyond just the plain bandwidth measurements. Yeah, so there's even more data that we can use to inform protocol decisions, for example, which is one of our main goals. So thank you.
Okay, thank you. And Yiannis, if you want to say some last remarks.
No.
No? Yeah, okay.
Thank you very much.
Thank you, Dennis and Yiannis, for amazing tool to analyze the P2P network. I think now it's time for...